available?
Okay, let's get started here. I'm glad and pleased to announce Lionel Antognelli, who's be presenting the topic around safety and systems engineering today. An exciting topic. I'm looking forward for it. Just to give a quick background, Lionel serves as a vice president for engineering projects at Orano, USA. He also leads engineering, license, and product management organization. He's responsible for guiding all phases of major nuclear projects, providing strategic direction and overseeing development of key engineering strategies and functions. That's impressive. He has about 25 years of experience and has done many projects to conclusion, and his experience and technical managerial expertise has been recognized. He has been successfully launched innovative solutions that impact critical business needs, and he possesses a deep understanding of lifecycle stage for large, safety-critical system development. He also holds Masters of Engineering degree from ISET. He's CSEP certified, that is Certified Systems Engineering, and a PMP certified, and he has earned several professional certificates from MIT. With that, I'll hand it over to Lionel, and Lionel, off to you.
Hey, thank you, Arish. So yeah, good evening, everyone. I'm really glad to be here today with you. So hopefully we can have a good discussion. So I'm going to start talking about system and how basically safety relates to system engineering, and I think that there is a lot of good story out there that we can definitely get some good lessons learned. So I will try to show you a couple of those lessons learned, and hopefully being able to provide a little bit of information and try to find some way to better integrate safety and system engineering as we are moving forward. So I'm sorry, I cannot move that. So let me go out during the presentation. Okay, and then going to move to the next slide. Okay, now it's working. Perfect. So in this presentation, I think I'm going to suggest that safety must be embedded into system engineering from the very beginning, and how proactive rather than reactive approach to safety improve the overall system safety, system resilience, and reduce the overall risk. So the objective of today's discussion is really to highlight the critical role of safety in the system engineering process. So I will try to present and discuss with you how safety is intrinsically linked to system engineering, and why it should not be treated separately. Then I will try to demonstrate the impact of safety consideration on design and lifecycle management, ensuring safer operation throughout system lifecycle. Then I will go and talk about a couple of real world case study, and then I will continue with talking about common pitfalls and lessons learned. So the agenda. So let's take a quick look at that. So I will start by introducing safety and system engineering, with definition of the key terms, and trying to establish the relationship between safety and system engineering, and explore how safety consideration influence system design and lifecycle management. And then we will dive into a few real world case studies. So the first one I've chosen is a chemical reactor accident, which will highlight how poor requirements and a lack of holistic safety view can lead to a disaster. Then I will talk about the well-known TERAC-25 radiation machine, which is more focused on software safety issue. And then we'll talk quickly about another example about hydraulic power plant failure, which will teach us about the risk of redundant system failing simultaneously. And then we will wrap the discussion by some larger lessons learned, and hopefully I hope that there will be some key takeaways that we can integrate safety more efficiently into our own work. Okay. So let's move on. So let's start by a few definitions. So obviously I'm using the INCOSE handbook for the first definition, and basically what it's saying is that system safety engineering aims to reduce and mitigate hazards within a system to an acceptable level of risk, and this applies to people, assets, and the larger environment. So maybe just a key takeaway that I really want to highlight. So safety is not just about making individual components reliable. Okay, so we will talk more about that, but a system, we really need to make sure that a system can fail catastrophically even when all the components function as designed. Safety is an emergent property. It results from interaction between system elements and external conditions. And when we are conducting safety analysis, I think that's also an important takeaway. I mean, we have to realize that there is a specific context, right? So depending on where in the life cycle you are not necessarily going to aim for the same results. So if you are in development phase, basically the question that you ask is, how do we make the system safe, right? If you are in operation, usually the question is, how do we keep the system safe, assuming it was safe in the first place. And then the last part is, when you do certification of your system, the question is more like, how do we demonstrate to regulators that the system is safe? So it's really important to understand that depending on the context, you might want to think about, safety in a kind of a different way, even if, at the end of the day, the goal remains the same. Sorry, you have potentially different tools and different methods that you can use. So let's talk quickly about the main relationships between safety and system engineering. So modern engineering projects can involve hundreds or even thousands of people, from designer and developer to operator and maintenance team. So ensuring safety requires that the right information is available to the right people at the right time. And that's really a critical part. Traditional design process often separate safety and engineering, but to me that's a mistake, and unfortunately that's something that it's happening pretty much every day. Safety must be integrated into the engineering process from day one. The difference in a safety-guided design approach is that hazard analysis is conducted throughout the process. Instead of identifying safety risk after a system is built, we design safety into the system itself. So what does that mean? Well, I guess a few points. The first one is that safety constraints must be factored into design decision and not just evaluated after the fact. Second, system requirements must be derived from the safety analysis. And third, system analysis must be iterative, adapting to the system modification over time. So you should really not see, all the safety analysis and all of that in a static ways. Actually, it should be very dynamic, and it's not something that you do once and then you are done. That's something that you are supposed to really, iterate as you are moving forward throughout the development phase, and then during operation until basically the end of your system. So how safety consideration can influence system design and lifecycle management. So basically, I'm just going to go quickly through a couple of bullet points, but system safety, emphasize building in safety and not adding it to a completed design. System safety deal with the system as a whole rather than with subsystem and components. So safety, again, it's a system property, not a component property. So that's a really critical point that I know that a lot of people, when I'm talking with them, early on are confused. There is not such a thing as a safe component. I mean, that's really a safety property. System safety takes a larger view of other than just failure. So unfortunately, most of the time, serious accidents can occur even if all the components are functioning exactly as specified. And lastly, system safety recognizes the importance of trade-off and conflict in system design. So that's another good example about why you should really trying to incorporate as close as you can all the safety and your system engineering efforts. So now let's move to a few case studies. The first one, I'm not going to go in too much detail. I'm just going to go through those case studies. If we have some question, we can spend more time at the end of the meeting. So the first case study, it's about it's a well-known story. It's about a chemical reactor accident. So basically, the situation was that you have a reactor, and you, in order to make your system working, you have to add some catalyst into your reactor. This catalyst was, the flow of this catalyst was controlled by a specific valve, and this valve was controlled by a computer. So what did happen? So first of all, as you can see, this is a system which is managed by a software. So you have your programmer designing your software. Basically, they need requirements, right? So they were told that if any fault occur in the system, they were to leave all control variables as they were. Okay. So this is what they did. And basically, on one occasion, what happened is that the gearbox sent a signal about a low oil level. Okay, and that was, as you can imagine, that was not part at all. That has no influence at all into the process. However, because of the way the requirements were created, the computer sent the signal to the valve, and basically the situation was that no more control on this valve was occurring. At the same time, the catalyst was flowing into the reactor, and basically the situation was that the reactor overheated, the release valve opened, and chemical content were discharged into the atmosphere. So this accident was really a result of a sequence of events, and as I was mentioning before, none of which involved a component failure. So on this specific case, there was no component failure. However, at the end of the day, we still get an accident. As I told, the requirements as specified did not prevent the occurrence of an hazardous system state. So this kind of situation, I think it's a good example that you need to look at the larger system and really to account for all the behavior of the system. It's really it's again, I mean, safety is not a component characteristic. It's really a way that components interact with each other that can lead to a state which is not safe. Let's move on to the second case study. I'm sure that most of you know that. I think it's from the Incosian book. So this time, so we are talking about a medical device, a Terac-25, which is a radiation therapy machine. What happened is that back in the 80s, a couple of patients were severely injured or died due to overdose of radiation. The conclusion after the investigation was that the leading factor was some software error. So a few contributing factors, so lack of proper safety mechanism in software, inadequate testing and validation processes, and reliance on operator to manually monitor safety despite software error. So what are the lessons learned with this example? The first one, I guess, is obviously an overconfidence in software. The first safety analysis of the Terac-25 system did not include software. So that seems kind of crazy situation, knowing that pretty much all the safety responsibility was managed directly by the software. But as the investigation showed, they didn't account for the software in the initial safety analysis. The second important point is software reuse. So there was kind of a wrong assumption that reusing previous software, which was the case in this example, will increase safety because the software will have been, tested extensively on previous machines. I think we can add that we had unrealistic risk assessment, so probability risk assessment, which is the way that most of and it's a very well method to assess the risk. Sometimes it's not the best approach, especially when you have software in the loop. I think it's a pretty good approach when you have mechanical system, but as soon as you start adding software in the loop, that's a different story, and I will talk a little bit more about that later. And then the last point, again, it's confusing reliability with safety. Okay, it's not because we have a reliable system that necessarily mean that it's a safe system. So those two concepts are very different. Then the last case study. That's probably a less known accident that occurred back in 2005. So that was basically an hydraulic power plant that was overtopped during the pumping cycle. So basically, you pump the water into the tank, and then you discharge the water, and you generate electricity like that. So that was the principle of this power plant. And what happened on that day in December 2005 is that due to some specific situation, the reservoir was overfilled, and basically it break at some point, and I mean, hopefully they didn't get a lot of people injured, but a lot of water was rushing through an empty campground just below that, and it destroyed a couple of homes in that area. So the consequences were not that bad, but could have been pretty bad. So what did happen? So to reduce the risk of overtopping, so water level were monitored with pressure transducer. Conductivity probes were also used in case of problem with pressure transducer. A PLC was designated to command the shutdown of the pump. And then there was a delay before the alarm was sound to account for water movement. So that was basically the setup of the system. So why did we get this accident? So couple of different reasons. The first one, it was found after the fact that the pressure transducer became detached and gave an erroneous reading. Also, one of the two conductivity probes was placed too high. And so what happened with those two events is that basically within the 60-second delay, the pump were never shut down, and it was too late, and basically the level of water was too high, and that led to the accident. So couple of lessons learned here. Designing out the hazard is more effective in most cases than safety device, right? So you can ask the question why the system wasn't designed in the first place to withstand the kind of maximum level of water, and that could be driven by a lot of different factors during the development of the project. Redundancy may provide a false sense of security, and may not truly exist when we need it, right? So again, that's kind of a common situation where you develop a program, you don't really think about safety. You don't really think about that from safety perspective. Then at some point down the road, you realize that you need to do something to prevent something from happening, and then you start plugging some safety add-on, and sometimes those analyses kind of push you to add redundancy, right? And so you can end up in a situation where you have a redundancy that you feel good about it, but in reality, when you take a broader look at that, do you really have redundancy, right? It's not because you have two sensors to make sure that something is not going to happen that it will not happen, right? So you have to think about common cause failure. You have to think about a lot of things. Again, if you think about that early in the development, you should find a way to avoid some complexity, and adding more safety device is most of the time not the best solution. Okay, so I want to spend a little bit more time on those last few slides, because I think that this is kind of a summary of a lot of lessons learned, and common pitfalls that I've been able to see in my experience, but also when you look into the literature, you can find pretty much the same thing repeating over and over. So it's kind of I think that's we have 3 slides here. It's kind of high-level summary of common mistakes. And I think that that should hopefully provide some good information for you. So let's start. So some critical lessons learned here. So first one, safety must be part of the engineering process from the beginning. I know that I already mentioned that several times, but I cannot emphasize that enough. If safety is considered late in development, it's often results in costly redesign or add-on protection mechanisms that are less effective than inherent safety measures. Probability risk assessments, so PRA, have limitation. I know that this is used in a lot of different industries in supporting a lot of safety analysis. And I mean, we need to make sure that we understand that while probabilistic risk assessment can help estimate failure likelihood, they should not be the sole decision-making tool, and especially for digital systems, where you can make assumptions about independence of failure that may not be true. Okay, so again, I mean, if you have a very mechanical system, that's probably a good tool that you can use. If you are working on kind of more modern digital system, that could be a starting point, but that's definitely not the only tool that you should use, because this tool has limitations. Third one, safety-related design decision must be well documented. Okay, especially if you are working on a large project that's going to last for 10, 20, 30 years. You should not think about making safety decision just for the sake of the development or the certification. When change occur, and they will occur, if the original safety constraints and assumptions are not properly documented, teams might unintentionally introduce new risks during the next phase of the project. Again, that seems to be kind of straightforward, but it's not that easy. And again, that's a good segue to going back to the system engineering, right? You need to define your constraints and your assumption. You need to find a way that you can keep track of all of that. And so that's very critical point if you want to make sure that your system is going to be safe and to remain safe during all the system lifecycle. And kind of on the same note, a system that was once considered safe, can become unsafe over time due to a lot of things. Could be environmental changes, could be operational shifts, could be modification. So you should really look at that from a very dynamic situation and not a static point of view. So this is why continuous reassessment of safety is critical. So on the second slide here, so another key consideration is definitely human factors. Technical and social aspects must be considered together. Many system failure involve human error, but rather than blaming operators, we must ask, did the system design set them up for success? Can give you another example. I'm sure that most of you have experienced that, but let's say that you design an interface and this interface is confusing, or if you have warning alarms that sounds too frequently and get ignored, then the system itself is part of the problem, right? So I know that sometimes it's easy to blame, the people doing the operation, but we should really ask ourselves, is there a way that, the system is not designed well enough that can become confusing for the operator and that can lead to some accident? And there is a lot of example in the literature that you can find that exactly on this specific topic. Another point, a system must be designed as a whole to allow resilient behavior. Okay, we cannot just focusing on improving one part, like ensuring component reliability. That will not improve your safety. Okay, again, reliability is not synonymous of safety. Those are two different concepts. The interaction between different parts of the system must be actively managed to maintain overall safety. We should avoid designing systems that exceed our ability to intellectually manage them. So modern systems are highly interconnected and tightly coupled, which make predicting all possible failure mode incredibly difficult. I think that's one of the biggest challenges that probably most of you are experiencing today. And there is not a single answer. There is not a single best way to solve this question. But as systems grow more complex, ensuring safety requires simplification where possible, and the use of robust system mechanisms. So keeping things simple is probably the best way to make a system safe. I know that's not all the time easy to do that, but you should really ask yourself when you start, developing your system and you start becoming in a situation where you have a lot of interconnection, you have a lot of tightly coupled system. At some point, how can you make your safety analysis? How are you going to do all your verification and validation? So we need to find a way to simplify the system as much as possible, and that will definitely help, not only from a safety perspective, but that will also help to save cost and reduce the overall risk on the project. So ultimately, a system-first mindset doesn't just protect people, but it can also save costs by reducing expensive redesign and preventing failure that can lead to legal and financial consequences. And on this last slide, a major challenge in engineering is unnecessary complexity, okay, which often arises when safety is not considered early in the design process. So as I was saying on the previous slide, just going to expand a little bit here, but adding unnecessary complexity makes the system more fragile. If safety is introduced too late, it often results in extra redundancy or protection devices being added onto an already complex system. However, these additional safety mechanisms can introduce new failure mode, making the system even harder to manage. So that's kind of the crazy situation when you can end up at some point where you start designing your system, you don't do your safety analysis upfront, and then down the road you realize that you have something that you have to correct, but basically too late because you have already committed a lot to your overall design. And then you start adding feature, you start adding components, and your life becomes more and more difficult because maybe you are going to be able to solve some of your initial safety risk, but then you have to consider new ones, because you add, new feature, you add new components, and so you have to explore more. And so, this scenario can go on for quite a bit. And again, at the end of the day, you might end up with a system which is not as safe as you might expect. Safety analysis must start in the earliest concept development stage. Okay, safety is not just a box to check at the end. Again, it needs to be continuously assessed from the first design sketches to the final disposal. And the best design prioritizes simplicity and robustness. Okay. As I said before, a tightly coupled system is much harder to make safe. Instead, we should strive for design that can tolerate failure gracefully. For example, if I'm going back to one of the previous examples, when I was talking about the TRAC 25 case, safety was dependent on the software functioning perfectly. A better design would have included, hardware interlocked as an independent safety feature. That would most likely have solved the safety issue they have with the software. But again, you need to take that into consideration early on. Otherwise, it's going to be pretty difficult for you to change the design late in the life cycle. So, few conclusion. I think that integration of safety into system engineering. So I think that hopefully I've been able to talk about a couple of examples talking about safety requirements. So how do you include your safety requirements in your overall system engineering approach? Making sure that you understand from the top how you are going to relate and to define the behavior and the different state of your system, and how all of that is going to be incorporated into your safety analysis. All of that is really key if you want to be able to develop a safe system and to avoid overcost, late change in your design. So basically, so by adopting those best practices and framework, organization can mitigate risk and enhance the overall safety performance of the project. So safety, and I will end by that. I think that safety is not always the most expensive option. Okay, know that in the mind of some people, maybe sometimes even project manager might see safety as kind of something that you have to do on the side, with kind of a wrong understanding that safety means basically more cost, and in many cases that's exactly the opposite. In many cases, a well-designed safe system is also more cost-effective over its lifetime. And so that's really something that needs to be understood, not only by system engineer, but from broader perspective, even from project manager and up to the company level. I think that's pretty much it for me. I put a couple of references at the end. If you are curious and want to get a little bit more information, and yeah, that will conclude the presentation, and we can open the Q&A session if you want.
There are two questions on the chat window, Lionel.
Okay, I don't see them now, so let me open.
I can read it for you if you want
Okay,
to.
okay, no, it's okay. It's just I had to switch my screen, so that's why. So those questions: how does the system implementation construction impact system safety? Well, I mean that's a good question. Well, when you are into your construction phase, you know, I will try to keep things simple, right? It's pretty much already too late, right? You have already committed to your system design. So if you start thinking about system safety when you are in construction phase, it's probably not a good news. Again, I mean, going back to the system engineering approach, I mean, I'm sure that you are all very well aware about this diagram on the handbook when when you start making change very early in the process, it doesn't cost a lot. Now, if you are waiting until construction to start thinking about safety, of course, you are going to have some tough decision to make. So my answer will be that you really don't want to wait construction to start thinking about that, and making sure that you have in your safety analysis from the very beginning incorporated as much as you can. Now, I mean, on the real life project, there are always changes. There are always things that you cannot anticipate, and that's fine. I think that's especially very large project. It could be very challenging. But again, as I was saying in my presentation, you really need, when you do your safety analysis, you really need to record all the constraints and all the assumptions, right? So if you do that early on, even if you are missing some steps, even if you are missing some scenario, right, accident scenario, whatever down the road, that way you can come back to your initial safety analysis. You can look at your constraints, you can look at your assumption, and then you can make better decision based on that, right? If you don't do that, again, especially if you are working on a very large project after a couple of years, people are moving, is going to be extremely difficult. So that's a really important lesson learned, that you have ready to record all those decisions with the proper assumption and understanding the proper constraints. Because again, everything is changing over time, and so what is true today might not be true tomorrow. Another question. So does the need to present this lecture in 2020 show how bad the system engineering process is? Well, I don't know. I think that there is a way. I think this is not my message. I think I talked during this presentation about some examples just to illustrate some situation, because I think it's better to show some example and to try to avoid falling in the same pitfalls. However, there is a lot of projects I think following this kind of guidance. I think they are pretty successful. So yeah, I think that's kind of my message today or tonight. I think that if you pay attention from the very early development, and if you would really implement a good system engineering approach, tracking your requirement, at the same time doing your safety analysis and using the output of the safety analysis as input to your requirement. And again, as I said, I mean, you should not, and I think that this is the issue that I've seen in with some company, that it's a very static way, right? There is a kind of a mindset that you do it once and then you are done. And then that's obviously not the situation, right? It's obviously a very iterative process. And you know, especially on large projects, I mean, you have to iterate and you have to go through different design phases, you know, and as your design mature, your safety analysis mature, and then you go to the next cycle. And I think that if you have a way that you can manage that, you can definitely be successful, and at least you can reduce the risk on your project, and you can reduce the change down the road. I think that should be one of the major goals for every system engineer or project manager, is what you can do early on to reduce late changes, because we all know that late changes is pretty bad, and that's what impacts the most your program. Okay. Is there anything else?
There was another question about case study 3. It says, how does the design team recognize a potential hazard and determine how to mitigate it? So I think this goes to a question I had, Lionel, which is, you know, given some of the deficiencies in the traditional FMEA, and your point around failure doesn't, you know, mean that that you've addressed the safety situation. What tools would you recommend using? What have you found useful for the design team to use to identify potential hazards?
Well, I mean, it's a tough question, because that's really depend on, you know, the context and the situation. I mean, what type of system are you working on? But I would say my recommendation would be to do not use only one tool, right? I think that especially if you are working on a kind of large system, and especially if you have kind of digital system, you should really not using only one approach, right? Again, I mean, some of those methods or approach are good, because I mean, some of them are more like, you know, bottom up. They are really focusing on, you know, the component, and so what happens if I have one component that is not going to work correctly or as anticipated, right? So I mean, sure, you have to do that, right? And those methods will help you try to identify, you know, the what will happen if you have a specific situation, and you have one sensor that for any reason is not working anymore. So those methods are really good to do that, right? However, those methods are not good at looking at the broader picture. Okay. So those methods will not show you basically, or will not identify what would happen if you have basically bad behavior, right? So let's assume that you don't have any components failing, right? As I was showing the presentation, most of the accidents, you know, the big accident that we are all aware of, in most of the cases, there is no component failure. It's really a question of behavior, okay? And that is much more difficult to track. So there are methods that are out there. I think STPA is a good one that can look at a more broader approach, and they are really looking at the control. So what type of control, and what will happen if I, you know, for some reason I cannot control, you know, this system the way I'm supposed to control it. And it could be due to a component failure, but it could be also due to, let's say, bad requirements, right? So the software guy basically perform or release his software based on those requirements, but the requirement was not what it's supposed to do. And so that's more about the behavior and the dynamic of the system. And so there are some methods that are better suited to this kind of safety analysis. So yeah, it's kind of a long answer for your question. But
yeah, no, that makes sense.
I think in a nutshell, I will say do not use only one approach. You have to try different approach, and ideally you will want to have some bottom up approach and some top down.
Looks like those are the questions that we had. There's no any more questions. Anybody has any thoughts? Prashant?
Yeah, I have a request.
Go ahead.
I started a podcast on systems thinking and systems engineering using AI. And one of the things I do is I take a set of slides and I let the AI discuss the ramifications of what's in the slides. So I'd like a set of slides for this talk so I can use it in the podcast. May I have one and permission to use it?
Sure. I think the slides are on the, and correct me if I'm wrong, Mike or Ashush, but I think the slides are available on the.
Yes, I think Sam has already posted the slides.
Yeah.
On the webpage.
Whose webpage?
In those.
Sorry, I believe the slides are on Basecamp. However,
Basecamp, sorry.
Yeah, if you're okay, we can also post it on the website as well.
Sure. Yeah, I mean, that's there is no proprietary information or nothing. So please feel free to share that.
Well, yeah, I guess one that gets posted, well, typically with two places. One's the website and the other one is our YouTube area. That'd be the video, and if we have slides, then what? Then it gets posted as well, correct, Sam?
Yeah.
Okay, so I don't know how fast this will get turned around though. So it may take a couple of days.
Oh, if you could send me the link to the YouTube video, what I do in that case is in the wording that describes the content of the podcast, I put a link to the original presentation so people can go back to it and view it.
Oh, okay. But I think that's typically what we do, but I don't know how fast we turn around the video.
Well,
Unless Sam, if you can, well, I don't know, it's kind of strange just to post the
there's no rush.
slides, start. Okay, all right. Okay, I didn't know how soon you may have needed it, so.
No, I've got stuff lined up for the next month.
Oh, okay.
I put the podcast title in the chat. Systems
Okay.
Thinking and Beyond.
Oh, okay.
You can find it on Apple, YouTube, and my website.
Okay. There's no other questions. Thanks a lot, Lionel, and great insight. Thank you so much for being with us and providing this insight. Appreciate your talk, and we'll stay in touch.
Thank you.
Thanks, everybody.
one.
Good night.
Great,
Bye.
thank you.
Bye.
Good night.